Hi, so this is from homework 2. This is problem 1, and we're going to use Dr. File's 4-step strategy to solve a force problem. So this is a very classic kind of problem in physics, at least when you're learning how to do force problems. We've got a man with a mass of 82 kilograms standing on a bathroom scale in an elevator, which sounds a little contrived, but honestly it is the best way to do these things. The elevator is accelerating downwards at 1.70 meters per second squared, so we want to figure out what the scale reads in newtons. So important to remember that scales, they don't actually read weight all the time, but they do always read normal force. They're telling you how much they're pressing back on the thing. So in a problem like this, first thing to do, step, what are we solving for and what units do we expect it to have? So we're solving for normal force, and it's a force, which means we expect it to have units of newtons. Next, we go on to step 1, and all year long, step 1 is going to be make a sketch. So we just want to picture, so we have a clear idea of what's going on here. So here's what our sketch is going to look like. We have an elevator. There's a scale in the elevator. There's a man standing on the scale in the elevator. Oop. His face got a little messy. Sorry, I'm not so good with this pen. Okay. Funny looking guy, but it'll do. Let's see. I'm assuming there's a cable attached to this elevator. Let's assume he's going down. So we've got speed lines. The man has a mass of 82 kilograms. And let's see, the scale is accelerating downwards at 1.70 meters per second squared. So I'm going to write A is equal to 1.70 meters per second squared. Now he's accelerating downwards, so it might be tempting to write in negative 1.70 meters per second squared, but I'm not going to do that. I'm just going to write it like that, and I'm going to draw a little arrow to remind me that he's actually accelerating downwards. So that's how we do step 1. On to step 2. So in a force problem, step 2 is what's called a free body diagram, or FBD. So this is actually a kind of sketch, but it's a very particular kind of sketch. All you're doing is, well, let me put it this way. You're turning your object into a box. So the man is now a box. And to this box, we're only attaching forces. So what forces are acting on this man? He's got his weight going down. So weight is F sub g, force due to gravity, and that is equal to mg. And he's touching the scale, so that means the scale is putting a normal force on him going up. So that's all we need from our free body diagram. We don't attach accelerations, we don't attach masses. It's very important that in a free body diagram, the only thing that you're attaching, the only thing you attach to the box are forces. So only forces, no masses, no accelerations, no velocities, no nothing else. All the other things can go in your sketch, but in your free body diagram, only forces. So let me pick a color we haven't used yet. I guess we're back to black. All right, I've got a limited color palette here. So your next step is going to be Newton's second law. So Newton's second law is the most important thing you will learn in physics all year. So that's F equals ma. So to actually do this, we've got to be a little bit more particular. So this is actually going to end up being sigma F. So the sum of the forces acting on this mass times, the sum of the forces acting on this mass. And it's very important in step 3 that all of your vectors wear these special vector hats. That might seem a little bit weird, but believe me, there's a reason for it. So sigma F is equal to m times a, mass times acceleration. So the right side of this equation is going to be the mass times the acceleration. So for now, I'm just going to write equals ma with a hat on it, and the left side, sigma f. So to figure out what that term is going to be, go back to your free body diagram, grab all of your forces, put hats on them, and plus them together. So this side is going to end up being F sub n with a hat plus F sub g with a hat. So again, very important in this step, all your forces wear hats, and all your forces get plussed together. So regardless of which way they're going, they're all going to get pluses. So now we're on to step 4, which is the math. So the first part of math is taking the vector hats off and putting in signs for things. So the first thing we're going to get to is F sub n, the normal force. So if I look back at step 2, that's going up. So that means when I take the hat off it, it gets a plus. So the plus is just implied, so I'm not going to actually write it in. But take the hat off of F sub n, that's going up, so that gets a plus. F sub g is going down. So when I take the hat off of F sub g, it gets a minus. So that is now minus F sub g. And this is equal to, excuse me, m times a. So a had a hat on it. Acceleration is a vector. So when I take the hat off, I've got to figure out what sign it gets. So remember back to our step 1, it's going down. So that means when I take the hat off of this, it's going to get a minus sign. So m times minus a. So I'm going to rewrite that really quickly as minus ma, just makes it easier to write. So F sub n minus F sub g is equal to minus ma. Now the thing I'm trying to solve for is F sub n. So to do that, I'm going to add F sub g to both sides. That's going to leave me with F sub n is equal to minus ma plus F sub g. Now if you look at the footer of all of the homeworks, there's a formula for F sub g. So when you're doing these homeworks, you have to keep subbing in this one term. So this is going to give us equals minus ma plus, our term for F sub g is really mg. So now we go to the numbers, and I think I'm probably going to run out of room here, but this is going to give us F sub n is equal to minus, his mass is 82 kilograms, the acceleration that he's experiencing is this number here, 1.70 meters per second squared, plus m is his mass again, 82.0, sorry, that's a 0.0 kilograms. And then for g, that's going to end up being 9.8 meters per second squared. And it's a positive 9.8 meters per second squared, which might be a little confusing because it wasn't that way when we were doing kinematics. But trust me and just go with that for now. So now we just have to do all the math. If we get this right in the calculator, we're going to end up with F sub n is equal to 664.2 newtons. And I'm actually keeping more significant figures than I'm really supposed to, but that's okay. So I put a box around it, and then I quickly go back and I do a step So the thing I was looking for was the normal force. I expected it to have units of newtons. If I go back to my answer, I do have normal force, I do have it in units of newtons. Now does that number make sense? 664.2 newtons, is that a reasonable normal force? This is hard because we don't often in our everyday lives deal with forces in newtons, but trust me, that is a reasonable kind of value for that. So this passes step so that makes sense. Now, let's go back and quickly think of all the things we've just done here. How does this strategy work? First of all, it's a 4-step strategy, but of course my 4-step strategies have extra things. My 4-step strategies always start with step huh. So what are we looking for? What units do we expect it to have? Then we get to step 1. All year long, step 1 is make a sketch. So just draw a picture, make sure you have a clear idea of what's going on. You make your sketch. Step 2 is your free body diagram. So a free body diagram is a special kind of sketch. When you're doing your free body diagram, you turn your object into a box, and to that box you only attach forces. So you only have forces attached to the box in the free body diagram. You leave out things like acceleration. That's not a force, so that doesn't go in there. And you leave out things like mass, also not a force, so that doesn't go in the free body diagram. So then we go on to step 3. Step 3 is always going to start with writing Newton's second law. So we're writing it in kind of a particular way. Newton's second law is F equals ma, but really it's going to be sigma F, the sum of the forces, is equal to mass times acceleration. And in step 3, all of your vectors wear hats. So they've all got these funny hats going on here. Oop, I didn't mean to move that around. Sorry, getting the hang of this touch screen. So yeah, in step 3, all of your vectors wear hats, which sounds weird, but trust me, there is a reason for it. So in the second line, over here, what you do is go back for sigma F, go back to your free body diagram, grab all of your forces, put hats on all of your forces, and plus them together. So in step 3, all of the forces wear hats, and all of the forces get plus together. And in this case, the right side just stays equals ma with a hat. Step 4 is the math. The first part of math in a force problem is going to be take the hats off and assign the signs. So when I take the hat off of F sub n, I look back at my free body diagram, and I have F sub n, that was going up. So when I take the hat off of that one gets a plus. F sub g, this guy right here, that was going down. So when I take the hat off of that guy, it gets a minus. So I've got this minus right here. And then to the right side, when I take the hat off of A, remember A in this problem happened to be going down, so that gets a minus as well. So hopefully this helps. Oh, there's one more thing to point out there. So it might be confusing why, when I got down to here, F sub g is now positive 9.8 meters per second squared. The acceleration due to gravity is still down, but we don't write it as the negative number because we've already handled the fact that gravity is going down right at this point right here. When we took the hat off of F sub g and saw that it was going down, we put in the minus sign. So that's how we handle the fact that gravity is going down. Basically, the hats are sort of an accounting trick. You want to make gravity down, so you want to put in the minus sign exactly one time, because if you accidentally put it in twice, you will have made it a positive thing. So that's why we do it. Hopefully this helps.